Hello all, welcome back. So in this video, we are going to learn about the risk categories. So let's start with M6, insecure authorization. Authorization is the act of checking that the identified individual has the permission necessary to perform the act. Authorization checks always immediately follow authentication of the incoming request from a mobile device. So examples include hidden endpoints and IDOS. So for example, let's say there's a user A and there's a user B. Now user A should not be able to view the documents of user B and vice versa. User B should also not be able to see the documents of user A. Now if this particular thing is happening, then there's an access control issue that is going on inside the mobile application. So this should be avoided. Or let's say idle. So let's say user A's personal documents are available on the internet. So if I just copy the link of user A's documents and paste it on a session wherein there's no login performed, I'm still able to see the user A's documents. Now that's what we call as an IDOT, that is an insecure direct object reference. Again, that comes under insecure authorization. So such things should not happen inside an application. The second one is client code quality. Now, code quality issues are found frequently within most mobile code. The primary goal is to execute foreign code within the mobile code's address space. So, for example, what happens is, let's say there's an application and this particular application is leaking certain memory data. Now, if the application is leaking certain memory data, then the issue of client code quality persists. Or let's say the application overflows the buffer memory, okay, and this particular memory gets leaked inside maybe the logs of the application or onto the application's front end. Again, if such things happen, then it can be a client code quality issue. Let's move on to M8, that is code tampering. An adversary can modify the code via malicious forms of the applications and host it inside third-party app stores. Then the attacker or an adversary can also trick the users into installing this application via phishing emails or other social engineering techniques. So for example, let's say there's a legitimate banking application and an adversary or an attacker can reverse engineer that particular application, tamper the code with it, and uploads this particular application on a third party store. And now the attacker has run a social engineering campaign. Okay, let's say a phishing campaign wherein the attacker sends you a mail stating that our application is down onto the Play Store, or our application of the Play Store has been hacked. Please use this particular link to download the new safe application. And you are a victim of the phishing email. You think that this email is from a legitimate source. You download the application, and now for you, the application is running smoothly. But at the back end, it is the tampered code that is happening. So, changing the certificate to bypass SSL pinning, or changing the API version, or tampering of the source code to perform some other malicious actions is or are all the examples of code tampering. Now, how do you prevent code tampering? You can prevent code tampering by a technique called as verifying the signature. Okay, so for example, before installing the application or after installing the application, all you have to do is you have to verify the signature of the compiled APK. So there's a process of installing an application. Before you install an application, the source code is compiled into an APK, and this APK is signed by a developer. Now the signature of the developer is very unique. Okay, it's unique for each and every developer. The application should have checks implemented stating that if the application has been signed by any XYZ signature, or the application has been signed by any XYZ party, the application is not going to run inside the mobile device. The application will only and only run if the APK has been signed by the legitimate developer or by the legitimate signature of the developer. So in this particular manner, you can stop the users from running a tampered code. or a tampered application, and you can save the users by being the victim of the attacker. So this is M8, that is code tampering. Let's move on to M9, reverse engineering. Now by default, all applications are susceptible to reverse engineering, okay? All mobile applications, especially Android. All Android applications can be reverse engineered very easily. Why is this the case? Because there's the source code that is converted or that is compiled to become the APK, and this particular APK is then installed onto your device. Now you can easily decompile the APK and get the source code file. So reverse engineering in Android and iOS is very simple. But how can you save from reverse engineering, or how can you protect your applications from not being able to understand by the attacker? Is something called as name changing. Okay, so what you can do is you can rename the function names, you can rename the variable names into something that is not understood by the attacker. Okay, and if your function names are something that is not understood by the attacker, let's say the function names are a b c d e, the attacker won't be able to know what a b c d e function does. And if the attacker won't be able to know what these function does, even if the attacker has the access to the source code, he won't be able to understand the logic of the application. So you can always save the applications reverse engineering by changing the variable and the function names. Now, certain other examples of reverse engineering include uh, reverse engineering the application to reveal information about the backend server. You can remove all the comments, you can remove all the information that can be leaking or that can help the attacker to craft a well-formed attack. You can remove the server's information, you can remove the developer's information, etc. So these are certain ways in which you can stop reverse engineering, or you can at least make reverse engineering difficult to understand. And let's come to the final one, that is extraneous functionality. So functionality that exposes information related to backend test, demo, staging or UAT environments should not be included in production build. So for example, let's say there's a hidden functionality inside an application to download configuration files. This is not required, right? This is not required. And if the attacker finds this particular functionality, he or she can download the configuration files and misuse those configuration files, right? So such functionality should not be enabled. Another example could be storing or saving all the data or showing up all the data inside the log files or the logs that are generated. Again, logs can be publicly available or publicly visible. So if the attacker gets hold of the device, he can view all the logs of that particular device. And if your application is storing too much data inside the logs, or it's storing too much data inside the logs, it's storing sensitive data inside the logs, the attacker may gain access to it. So having or storing sensitive data inside log files comes under extraneous functionality. So with this, we conclude this particular module. I hope you understood what is OWASP, what is OWASP top 10, what are the different categories of OWASP top 10 mobile 2016, and I hope you understood each and every category. You should always remember these all categories. These categories should be onto your fingertips. If anyone asks you at any time of the day, you should be able to recollect it, and you should be able to give them a firm answer that these are the categories and these are some of the examples of these categories. In the next section, we are going to start with the actual pen testing of the iOS application. We are first going to start with the static analysis of the iOS pen testing. And yes, that's it for this particular video.